let's start for the second part of the morning. So it's our pleasure to have with us Tero, who is coming from Finland, and we're going to present to us a bit of different subjects, which is like mixing magnetic domains with supercurrents. And
thank you for the organizers for the kind invitation to this event, and I'm sorry for yesterday's speakers for not being able to attend yesterday because it was came yesterday evening. I had a little bit of flu and need to move my arrival. I chose this topic because I'm quite excited about it. We submitted the work just last month, and this is the first time I'm talking about it in the meeting, so I had to prepare all the slides for this talk. It's maybe not entirely on the core of the workshop, but at least it has disorder inside it because they do disorder theory, and then it has some tooling materials. So it fits well enough, and I'm pretty sure that you have heard about this. Many of you have heard about the topic before, namely this magnetic domain wall control with the current, and I'm going to tell about work that was primarily done by Institut Pascal and who are postdocs in my group, and Sebastian Bergeret was heavily involved also in the work. Yes. Okay, I guess many of you have heard about Stuart Parkin's idea of building a new type of memory called the racetrack, where the idea is to have magnets which is in 3 dimensions in a way, and it then has multiple domains, and then by currents you would manipulate this domain, you move this domain all around, and then sort of be able to store more memory on a smaller space because you involve the 3rd dimension. The idea came by Parkin already more than 20 years ago. There have been multiple kind of stages to it, but we still don't have racetrack memory in our computers. There are lots of issues there, including, I think that one of the biggest ones is dissipation. You need actually quite large currents in order to move the domain. Now, recently, Stuart has been also working superconducting analog of this racetrack memory. His idea is that instead of using normal currents at low temperatures, you could use supercurrent, and then you would avoid this sort of strong dissipation in these systems. Now, this would maybe not be a solution to our memory storage for our laptops before we discovered room temperature superconductor, but it would actually be quite useful for sort of cryogenic computing application. For example, say now computers are in the stage of 200 qubits. If you want to go to thousands of qubits, you cannot do in the kind of current way anymore, where you do all your control lines from room temperature. What you need to do is that you build a computer at low temperature, and then that computer controls the classical computer. That computer then controls the quantum computer, and everything else in the computer in principle exists already, except for the memory. So the memory elements are not well established at cryogenic, let's say at Kelvin level temperatures. And then sort of if you would be able to magnetic memory controlled by currents, that would be possible sort of solution for that problem. Now, so the idea basically is here for the racetrack is that you have a current, let's say supercurrent, that then leads to a motion of the domain wall, so has a speed, and there's a linear relationship between the speed of the domain wall and the supercurrent. Now, there are still actually open questions. One of the issues in Stuart's work is that actually the theory doesn't quite exist yet. Maybe until now. There are two sort of big open questions. One is the fact that actually domain wall motion is because domain walls are not superconducting. There is Hilbert damping in magnets, and once the domain wall moves, that involves magnetization precession, and then the magnetization precession is damped by Hilbert damping. And therefore, you need to supply this power somewhere. Whereas in the usual ordinary supercurrent case, you don't. I mean, it's an equilibrium current, and you don't need any power. And then the question is, how can this equilibrium supercurrent maintain this domain wall motion? And then the second question is, okay, what is the mechanism supercurrent for this supercurrent domain wall torque, or let's say in a more technical way, so what determines the size and actually the sign of beta? How do we know that if we sort of run supercurrent in this direction, the domains could flow in one or the other direction? Okay, so these questions I tried to answer in my talk today. I will first show how you can get such a supercurrent domain wall torque, and actually precisely speaking, it's actually domain wall force from the inverse spin galvanic effect, and what that is. I will show how you can actually detect the domain wall motion by the fact that it generates voltage. I will discuss shortly how it will be used for glycemic memory, discuss the materials requirement, and then also touch the issue of power dissipation and heat. Now, this is not what we are doing now, but I first want to give you a sort of an image into your head on how current controlled domain wall motion might look like. The simplest version, which was discussed already in the 1980s by Heikkila and others for the normal state, was the following. Let's consider a ferromagnet that has a domain. But here, spins are pointing towards the screen, and here they are pointing outside of the screen. We apply a charge current along this wire because this is a ferromagnet that we are dealing with. This ferromagnet has spin polarization, and together with the charge current, there is a spin current. Okay. Now, if there's a domain wall in the system, it changes from one domain to the other. That flips the side of the spin current, and this difference between the spin currents actually amounts to a torque, and this torque sort of acts on the domain wall and then leads eventually to this motion. Okay, now there's a superconducting alternative sort of version of this similar idea. Sorry, by the way, nowadays so this is how things started in the early 2000s. Nowadays, people use spin orbit torques instead of this direct spin torques. But the idea is roughly similar. Now, supercurrent analogs for this effect have been discussed sort of some 6 years ago, where sort of instead of normal spin currents, one replaced this with supercurrents, but requiring triplet superconductivity. So meaning that the supercurrent carries spin. So instead of the sort of just the bulk triplet superconductor, which maybe exists in uranium platinum, but I'm not sure if uranium platinum for such devices, which you could only do it in a couple of places in the world to do that, and maybe it would be kind of hard. People have discussed the possibility of using sort of so-called long-range triplets in proximity setups with non-collinear magnetization. But actually, the way how this would work in a bulk system covered again. This also has issues that actually this requires sort of really stable arrangement of this non-collinear magnetization, which is not so simple. Instead of that, we actually propose to use so-called inverse spin galvanic effect to create this domain of motion. And I try to describe it here. So here we have a ferromatic insulator that has a domain wall in a similar way as previously, but I guess now the order of these things was reversed. Doesn't matter. On top of this, we put a thin film superconductor, so that sort of the thicknesses of these two materials are small compared to coherence length, and let's say this thickness of the ferromagnet should be also comparable, or thickness, or even smaller. Now, once we apply a current through the superconductor, it induces a phase gradient, and we call this phase gradient Qx. So this is the sort of externally applied phase gradient, which is the same on both sides of the domain. Now, if there is spin orbit coupling, then there is this magnetization will, together with the spin orbit coupling, will lead to another phase gradient, which is sort of what we call Q0, which is then sort of proportional to the magnetization direction. So it inverts sort of across the system. The fact that you generate a phase gradient from magnetization is called inverse spin galvanic effect, or it's called the spin galvanic effect, or the inverse Edelstein. There are many names for these things. Now, the reciprocal of that effect, generation of this Q0 here, is the fact that if you have this supercurrent running here, you generate an equilibrium spin in the spool at this interface, and this is now the spin galvanic. Far away from the interface, this equilibrium spin here. I mean, the spin direction, the magnetization directions here are chosen such that the equilibrium spin will be aligned with this magnetization far away from the domain wall, but at the domain wall, it's sort of anti-aligned with the magnetization and leads to a precession of this magnet. And this is actually the source of the domain wall force that leads to also the motion. Now, okay, and indeed, as I said, far away, the induced spin here is proportional to the magnetization, and this, if you look into detail, this means that there is no this long-range triplet that has been pursued in sort of other theories of physics before. And in fact, there's another consequence of this, which is related with this normal metal analog. Namely, there is no net torque domain. So actually, the electron torque on the domain wall is exactly equal to domain wall torque. Okay, so briefly about the spin galvanic effect, because there are many names for this. I just try to make sure that you kind of get what it is. It's this generation of the spontaneous phase gradient system in the absence of supercurrent in the superconductor. It's also called helical superconductivity, and it has a connection to the superconducting diode effect that has been discussed quite a lot recently. Namely, because now it sort of provides a direction in the absence of supercurrent to the superconductor, and therefore, if you apply a current either in this direction or in the opposite direction, this means that the current required to build superconductivity, or the largest possible current that you can maintain, is different in these two different directions. That's a superconductor. Okay, so basically, whatever system that provides this helical superconductivity from the magnetization can be used to generate our. Okay, so if we look a bit sort of closer, what this galvanic effect and its inverse are. So as I told already, if you have the magnetization, let's say in the out of plane direction, let's say in the y direction here, Then there is a polar vector describing the spin-orbit coupling, which is now the vector pointing between the fermionic insulator and the superconductor. Then there is an equilibrium phase gradient that is proportional to the vector product or product of these two vectors, namely the magnetization and the polar vector. And this is now in this third direction, and this is the current direction that we are considering. Now there is the inverse galvanic effect, where there is a supercurrent. There is again this polar vector, and this supercurrent then now creates a spin that is now sort of proportional to the vector product of these two vectors. Yeah. There are two versions of this depending on sort of what type of spin-orbit coupling you have in the system. There can be intrinsic spin-orbit coupling such as rush path that you would have in thin films or in 2D superconductors. In this case, sort of you just have this sort of excess spin everywhere in this wire. There can be also an extrinsic spin-orbit coupling that you would have in thin film metals. You would have niobium or lead or any other heavy metal. In this case, actually, the spin would be generated at the interface. Then there would be opposite spin at the opposite. But if you put the fermionic insulator, let's say in here, you only care about what spin you have in this case. So you will have the same effect in both cases. That the precise details on how they depend on the materials and on the geometry and so on differ. I will not discuss this unless you ask any question. I have a spare slide. Now, okay, the end and foot means not needed for understanding the talk. So just briefly about the theory, how we kind of the background theory of how we derive the domain wall dynamics related to supercurrents. We do this within the so-called nonlinear sigma model approach of superconductivity. You can also do a non-equilibrium version using Kelly-Sprint functions. And basically what we include are three parts of the action. So the first one is the nonlinear sigma model for the disordered superconductor, including spin-orbit coupling. The saddle point equation related with the action provides a so-called Usadal equation, which is known for. So this is disordered superconductivity. That was the disordered aspect of my talk. The ferromagnet is described by a ferromagnetic action that gives you spin action, gives the saddle point gives you the Landau-Lewis-Gilbert equation for the magnetization precession, and then there is a coupling between these two, which sort of describes, so it depends on both of this superconducting Q field and the magnetization, and this is described by local spin. Now, on top of this, you need to assume that there is a domain wall in the system. So, which means that you describe collective coordinate domain wall, namely the position of the domain wall, and then a conjugate, which is the sort of out of plane phase, and they have their dynamics, and actually the black parts of these equations are known since I guess 1980s already. But then what we derive is basically the torque and the force. Actually, the torque turns out to be zero in this arrangement that we described, but the force is fine. Now, that's the theory. Now, okay, 10 minutes. Now we can go back to kind of predictions, which are much simpler. Now, as I told, the inverse spin galvanic effect gives this spin accumulation on the interface. You can see that sort of outside the domain wall, the spin is sort of collinear with the magnetization, and therefore doesn't lead to any dynamic. If you have a spin, let's say that's like a field collinear with the magnet doesn't precess around that field. But inside the domain wall, it is non-collinear with the local magnetization because magnetization is rotating. And then sort of this rotating part starts to precess around the spin, and this precession together with damping leads to a force on the domain. Force is there even without damping, but then together with damping there is a speed motion of the domain wall. And actually the formula for the force is very, very simple. It's just the product of current, supercurrent, and this Q0, this sort of anomalous phase. On top of this, there is a domain wall drag quotient, which is slightly more complicated, but the most important part of this is this alpha, which is the Gilbert damping in the line. So it's the domain wall speed is basically dependent on damping. Now, and then the other factors are just the geometric factors. In this case, this is the domain wall size, and this is the. Now, if you solve for the domain wall dynamics fully, you find out that there are two regimes. There is a so-called Walker breakdown current. So below Walker breakdown, the domain wall just moves with a speed that is linear in the current. And then there is this Walker breakdown current where after which there is a nonlinearity. Yes. Now, if the domain wall is moving, actually it creates a voltage. And why that happens is sort of relatively simple to solve. As I told you, there is this helical phase Q0 that changes sign across the domain wall. Now, if the domain wall is moving, this means that the phase gradient sort of at the given position depends on time. Right? And now you can plot, let's say, the phase gradient as a function of position first at time t0, and then at time t0 plus delta t, and so that it goes from qx minus q0 to qx plus q0 sort of along the domain. Now, this means that the sort of phase difference between 2 points across this domain wall becomes time dependent, and that means that there is voltage. Okay. It actually turns out that the voltage is just proportional to the area of this pair. And again, this voltage is actually quite simple. It's just related to this Q0 against this anomalous phase gradient, and then the speed of the domain. So whenever you have, let's say, I showed you here the speed of the domain wall. Actually, this is also the size of the detected voltage. So domain wall motion actually leads to electrical resistance in the superconducting plate, which is of course a detectable feature. So actually, this is to be a full superconductor, and without any domain wall pinning, actually the voltage becomes non-zero. There is no critical current. It's actually never a true superconductor. This is of course a way to measure that the domain wall is moving, and actually you can do it locally. So you can imagine putting voltage probes along this wire, and then just measuring the voltage between adjacent probes. And at some point you see that, okay, now there is voltage, and then now there is no voltage once the domain wall passed. And okay, the side of the voltage is basically just given by this Q0 times the domain wall. The kind of the time sort of that it takes for this to happen is sort of basically the distance between these between these voltage probes and divided by the speed. Yeah, and then sort of there are lines coming on. Okay, so this would be kind of a signature of the domain wall motion. Since there is voltage and there is current, there is joule power. E equals IV. And so this is an non-equilibrium setting, and this means that you need power to maintain this domain wall motion. But actually, here the power comes only from the domain wall motion. In the normal state, the power would actually come mostly from maintaining the current through the wire. So this power is orders of magnitude smaller than in the normal state. Now, if there is local power, there is also heating. So you can sort of figure out how much heating there is by sort of solving a heat balance equation. We saw something like that already in the previous talk. Now the domain wall motion makes it kind of time dependent, but you can sort of ditch time dependence in make it position dependent, and you can sort of solve for the sort of increased temperature at the domain. I will give you a sort of an estimated magnitude. Now let's consider sort of in the remaining time so what happens if you have multiple domains. So does it work with racetrack memory? Now let's consider that there are two domains. So domain walls, so domain. If you apply a current from left to right, this domain wall moves to the right. This domain wall moves to the left. Okay, which actually means that the current tries to enforce sort of this spin in the entire system. So it doesn't quite work racetrack. You would like to move all the domain walls in the same direction. Okay, however, it does work for memory, because you can think that, let's assume that this part, this section of the system, if the wire is your memory element, and here, let's say this pin would mean that you have a memory 0, this and the other pin would be memory 1. And if you start from, let's say, 0, you can just apply some current pulse, you move the domain wall across this position, you get to kind of 1. And if you want to then switch it, you just drive the opposite current. So this would be a very fast memory right? And then actually you can use the voltage here to determine sort of when did the domain wall move past a certain region. Okay, actually it turns out, I can discuss this later in the discussion part, that there is a similar effect coming just simply from the stray field of the current or Ørsted field. Whether the spin-off mechanism dominates or not depends on parameters. We have estimated some materials where this could be seen. You can use, let's say, heavy metal superconductors with large spin hole angles, or semiconductor hybrids together with thermic insulators, which should have well-defined easy-axis homogeneous anisotropy and so on to avoid pinning. They should be good interfaces between those systems. You can imagine using super semi systems with air-controlled sulfide, ceramic insulator. You can also assume using cooling materials and so on. We have made some estimates of the sizes of the effects, and we kind of realized that getting 100 meters per second domain wall speeds should be realistic within sort of realistic current densities. Voltage is rather small that you measure, but I guess principle measurable. This also falls to the adiabatic limit where you can still kind of where you can forget about quantum particle generation. If you look at this heating that I discussed earlier, our estimate using air-green sulfide parameters is that at 1 Kelvin, the local temperature increase would be 1 millikelvin. Not too bad. Okay. I quickly compare normal state and then I'm done. So let's compare the normal domain wall torque. If you have a normal domain wall torque coming from current, there must be a metal somewhere because you pass a current, and therefore actually there is typically an extra Clipper damping from the magnetization due to this presence of this metal. Whereas in the superconducting state, the metal is conductor. There's a gap unless you believe Lorentz who talked about sort of subgap, but we know extra damping. So the Gilbert damping comes from phonon only. Much higher quality factor for permanence. Power dissipation in the normal state comes from everywhere. Superconductor only from the domain wall motion. Heating is much smaller in the superconducting case. Pinning is probably a problem in both cases, so you still need to make good materials. Fluctuations are probably a smaller problem in superconducting. And I end up here with the summary. And I just have to quickly avoid the position. So it's, if I know somebody would be the postdoc, is no, and I'm happy to discuss with you. Thank you very much. Some questions?
So
as far as I understand, your coupling term in the sigma model, it involves fields on the boundary, right? Because it's
Yes.
short range, like exchange. So I wonder how does this, for example, domain wall speed, how does it scale with the thickness? So you have coupling which is on the boundary, and you have two terms which are kind of okay, thin film, but you still integrate over the transverse direction.
Yeah, the thickness of ferromagnet goes into some of these sort of. I mean, the ferromagnet thickness should be smaller than the superconductor thickness, more or less. They both should be smaller than the coherent length, therefore. They should be thin terms.
Why should the ferromagnet thickness be smaller than superconductor thickness?
I mean, or comparable, let's say. But okay, let me try to remember what was the strain. In fact, yeah, actually, one of the points comes from this Hertz field effect. So here, the sort of, it turns out that we made an estimate of the sort of spin orbit effect or distortion field effect. So there's a field would also generate a similar type of domain motion. In order to get the spin orbit effect, it comes from the interface. So to make that dominate, you need to make the ferromagnet thickness small. But actually, otherwise, it doesn't matter. And actually, the distortion field effect is always there. It's just that sort of say the spin orbit mechanism just dominates or dominates. Otherwise, I think that.
More questions? If not, we can thank Tero again.